Given a state space representation of a system, we want to be able to solve for the state variables and the output variables as functions of time. So we're going to work on an example and show that how we could attain that solution using Laplace transformation. And the system we're going to work with is this rotational mechanical system with gearing. We've got an input torque on shaft with displacement theta 1. We've got a 5-to-1 gear ratio to the output shaft. And on that output shaft we have a moment of inertia, a damper, and a spring. And the displacement there is theta 2. So we also know, in order to solve for the state variables in the output, we have to know the input function. So our input torque tau, we're going to say for this example, is the unit step function. And also the initial conditions. The displacement of the shaft at time 0, the input shaft, is 10 radians. And the velocity, the angular velocity of the input shaft at time 0 is 0 radians per second. And again, well, for this example, I don't know if I mentioned it yet, but our output is theta 2, and we want to find that function of time. So let's start by drawing the equivalent mechanical system on the input shaft. So again, we've got the torque, and we'll have a moment of inertia, and that is equal to, well, I'll just draw it as JE. So that will be the reflected moment of inertia onto shaft 1, which has displacement theta 1. And then we've got damping and a spring constant. And we'll call the damping CE and the spring constant KE. Okay, so let's compute now the values for these parameters. So JE is, so we've got that source, the destination teeth divided by the source teeth squared. So that's 40 over 200 squared, and then multiply that by the moment of inertia here, so times 1, and that's just 1 over 25. And the equivalent damping is the same, so we've got 4 over 20 squared times 5, so that's just 5 over 25, so we end up with 1/5 for that value. And the equivalent spring constant is again just 1/5 squared times 4, so that's 4/5. Okay. Yeah, that's a mistake. It's not 4/5, it's 4 over 25. So 4 over 25 is KE. Alright, now we have values for that. And we could write the differential equation for this. So we'll take the sum of the forces and let that, or sum of the torques, and let that be equal to the mass times the acceleration. So we have the input torque minus CE times theta 1 dot minus KE times theta 1, and that's all equal to JE times theta 1 double dot. Okay, and what the next task is to choose our state variables. So let's go ahead and write our state vector. And this again is just a vector that's made up of the state variables. So we call it x bar. Well, we call it x, and the bar just indicates a vector. So we'll look at this equation to find out what our state variables are. We're going to pull out the variables in this differential equation that have their time derivatives in the equation also. So we've got this second order differential equation, and we see one variable is theta 1 and its time derivative is there. So theta 1 will be one of our state variables. And then we also have theta 1 dot with its time derivative. So theta 1 dot will be our other state variable. And we're going to call theta 1 dot, we're going to substitute omega 1. So we'll call omega 1 theta 1 dot. So now that we have our state variables, the next task is to write first order differential equations. And these will be our state equations. So we want first order differential equations for each state variable. and that looks like theta 1 dot, and that's just equal to omega 1, and omega 1 dot we just get from rearranging this equation, or really just dividing through by JE. So we have negative KE over JE times theta 1 minus CE divided by JE times omega 1 plus 1 over JE times tau. And we can substitute in our values for KE, JE for our effective impedances, and we get that this is negative 4 theta 1 minus 5 omega 1 plus 25 tau. So these are our two state equations. And then we also have an output equation. We want theta 2, and we want to have this in terms of linear combination of our state variables and input. And theta 2 is just the inverse of the gear ratio times theta 1. So we have 40 over 200 times theta 1. Okay. And now remember, we can write these in matrix form. So that looks like the time derivative of our state vector is A times the state vector plus B times the input vector, and our output is C times state vector plus D times the input vector. And I'll do that on the next sheet of paper. So rewriting our state and output equations in matrix form, we get that theta 1 dot and omega 1 dot is equal to, or are equal to, our matrix A, which is the first row is 0, 1, and the next row is negative 4, negative 5. So those get multiplied by the state vector, which is theta 1 and omega 1. And we also have B, which is our input matrix, times the input. So that's 0 and 25 makes up B, and our input vector is just, oops, well, we call it U, but in this case it's tau. Okay. And then our output equation, we have theta 2 is, so we need a matrix to multiply the input vector, or the state vector by, so that would look like 40 over 200, which is just 1/5, and 0. If we multiply that by theta 1 and omega 1, we can get theta 2. So there's our state equation and output equation in matrix form. And what we need to do now is to solve for theta 1, our state variables. So want to solve for theta 1 of t and omega 1 of t, and we're going to use Laplace transform. So we're going to use the Laplace transform of the state equations. Okay. So going back, the state equations they're right here. There are two state equations, and in matrix form it looks like this. So the Laplace transform of this is S times the Laplace transform of theta, so that'd be theta 1, minus the initial condition of theta 1. And that is equal to the Laplace transform of omega 1, so we'll write that capital omega 1. Now the Laplace transform of this equation, the Laplace transform of omega 1 dot is S times Laplace transform of omega 1 minus initial conditions of omega 1, and that's equal to negative 4 Laplace transform of theta 1 minus 5 Laplace transform of omega 1 plus 25 times Laplace transform of tau. So there are our two equations, our two-state equations, the Laplace transform of those equations. And we could write this in matrix form. So in matrix form, this looks like S times the Laplace transform of our state vector minus the initial condition vector is equal to matrix A times the Laplace transform of our state vector plus matrix B times the Laplace transform of our input vector. So now we want to rearrange to get Laplace transform of our state vector, which is just capital X bar. So to make that possible, we're going to substitute that S times the state vector is S times the identity matrix times the state vector. And just to show that this is allowable, S times the state vector looks like S theta 1, S omega 1, which we could factor out the S, theta 1, omega 1, factor out the variable S, which is how we had it written here. And we're going to set that equal to S times the identity matrix times the state vector. Oh, this is the Laplace transform of the state vector, so these should be capitalized. Oops. So this would be theta 1, omega 1. So these should be capitalized. I'll just kind of scribble over them. And this equals S times 0, 0, S times the Laplace transform of the state vector. Hopefully that screen had not been black for very long before I noticed it, which is S times theta 1 plus 0, 0 plus S times omega 1, which S theta 1, S omega 1. So all that was just to show that we can make this substitution here. So substituting that in and rearranging, we get that, well, I'll just make that substitution. S times I times the state vector, Laplace transform of the state vector, okay. And now we can group our x terms. So S times the identity matrix minus A times the Laplace transform of the state vector is equal to the initial condition vector plus B times the Laplace transform of the input. And now we can solve for the Laplace transform of the state vector. So capital X bar is Si minus A inverse times state vector at time 0 plus B times U. Okay. And also, so this will give us the solution for the Laplace transform of our state vector. And once we have the Laplace transform, then we can use inverse Laplace transform to get our state vector, our state variables as functions of time. So for our particular example, we'll know A, we'll know the initial conditions, and we'll know the Laplace transform of the input. We'll also know B. So we'll be able to get Laplace transform of the state vector. And when we want the output, we will take the Laplace transform of the output equation, so that gives us y. The Laplace transform of the output is C times Laplace transform of the state plus D times Laplace transform of the input. So now back to our example. We want to find the values for these matrices. So S times the identity matrix minus A is equal to, let's find the A matrix. Where do we have that written down? So here's our state space representation. State equation, output equation. And this gives us values for A and B. So Si minus A is equal to S minus 1, 4, s plus 5. Okay, so that's using values that we had here. And this matrix inverse is the adjoint of the matrix divided by the determinant of the matrix. And I'll go ahead and compute that. So the adjoint of this matrix will take we'll find the cofactors and then the transpose of that. So the cofactor of this is s plus 5, cofactor of this is negative 4, cofactor of that is 1, cofactor of this is s, and we need to take the transpose of that to get the adjoint. And then the determinant is just s times s plus 5 plus 4. So the inverse of this matrix is, we'll expand the determinant, so s squared plus 5s plus 4, 1 over that times the transpose of this matrix, so we have s plus 5, negative 4, 1, and s. Alright, and now the other matrix that we need whenever we're solving, see we found this term, and now we need to get this term that's in the square brackets. So the initial condition plus b times u. And we'll write that here. Initial condition vector plus b times the Laplace transform of u is, initial conditions were 10 for the displacement and 0 for the angular velocity. And b is 0 and 25. And u, the Laplace transform of our input, we said that our input was the unit step function. So oops, hope that hasn't been black long. The Laplace transform of the unit step function is just 1 over s. So this is all equal to 10 and then 25 over s. Okay, so now we're ready to compute the values for the state Laplace transform of the state vector. So let's write that again. Laplace transform of the state vector is si minus a inverse times x0 plus b times u, and that is going to be 1 over the determinant of that thing times, so now we need to multiply this matrix times this. So we end up with a 2 by 1 matrix, which is the dimension of our state vector. So this row times this vector, we get 10 times s plus 5 plus 25 over s, and this row times this vector, we get negative 40 plus 25. So there is the Laplace transform of our state vector. Let's just go ahead and we'll just solve for Laplace transform of theta 2. So this is the first row of the state vector, and that's equal to, I'm going to expand these out, so we have 10s plus 50 plus 25 over s divided by, and this factors this denominator here, this is s plus 4 times s plus 1. S plus 4 times s plus 1. And now we want to get rid of this 1 over s in the numerator. So this is 10s squared plus 50s plus 25 divided by s times s plus 4 times s plus 1. And partial fraction expansion, so that we can perform the inverse Laplace transform of this, is a over s plus b over s plus 4 plus c over s plus 1. A. So now it remains to calculate A, B, and C so that we can get the inverse Laplace value transform. So A is equal to 25 over 4. B is, we're going to plug in negative 4, so we have 10 times 16 minus 200 plus 25, and that's all over negative 4 times negative 3, and that is equal to negative 15 over 12, which is negative 5 over 4. C, we'll plug in negative 1, so we have 10 minus 50 plus 25 divided by negative 1 times 3, and that's negative 15 over negative 3, which is 5. So now we can find the inverse Laplace transform of these three terms, and we get, oops, I wrote theta 2, but this should be theta 1. Theta 1, because that was our state variable. My mistake. So I had over here, that our state variable, or state vector is theta 1 and omega 1. So Laplace transform of theta 1 is what we just found. And now take the inverse Laplace of that, we get theta 1 as a function of time is equal to A, which is 25 over 4, technically times the unit step function, but we're only interested in times greater than 0, so we'll leave that up, minus 5 fourths e to the negative 4t plus 5 e to the negative t. And this looks roughly like, so this would be theta, and this is theta 1, and this is time, so it starts off at 10 and ends up at 6.25. So this is how far the unit step torque, input torque, rotates the input shaft. And now our output, theta 2, we can use the Laplace transform of the output equation. So theta 2 is 1/5 0 theta 1 omega 1, which is 1/5 times Laplace transform of theta 1. So theta 2 is just theta 2 as a function of time is 1/5 theta 1 as a function of time. So that's equal to 5 fourths minus 1/4 e to the negative 4t plus e to the negative t. And that is the solution for finding the output to this rotational mechanical system using state space representation and the Laplace transform of the state equations. So we kind of recapped several things here, coming up with the equivalent system in order to get the differential equation on the input shaft, determining our state variables, theta 1 and omega 1, writing our two first-order differential equations for our two state variables, and then the output equation. And then what we did new was take the Laplace transform of our state space representation, or really and obtain the values that are necessary to get us the Laplace transform of our state vector. And so once we had those values, we found the Laplace transform of the state vector, and that allowed us to get the state variables, Laplace transform of the state variables. Take partial fraction expansion allows us to perform the inverse Laplace transform for our state variable. So that gave us theta 1 as a function of time. And from that we could get theta 2 also as a function of time.